The main cause of weather phenomena is an extreme rise in the surface temperature of tropical seas in the summertime. The resulting tropical cyclones act as valves that release heat accumulated in tropical regions. Cyclones form in nature using the second law of thermodynamics, which is confirmed by information theory and chaos theory, and can become dangerous if they turn into hurricanes. The sun's warming of the oceans sets atmospheric air in motion. This is called convection. It may be useful, here, to take a quick look at a laboratory experiment conducted by physicist Henri Bénard around 1900 that illustrates how the phenomena forms at sea. In its initial state, a liquid stagnates between two parallel planes at the same temperature. The liquid is in a thermodynamic state of equilibrium, point 0 in the figure. Now let's shift the equilibrium slightly by heating the lower wall. The system is maintained by an external source of energy, point 1. Near the point of equilibrium, the behavior is linear and involves thermal conduction, an irreversible phenomenon described by Fourier's law. Some energy dissipates, and entropy, which we'll call disorder for the sake of simplicity, measures this energy dissipation. Thermal energy is transferred by molecular collisions, with no transfer of material, from the hot wall to the cold wall, in accordance with the Clausius postulate. The fluid is churned by movements that are invisible to us. When the control parameter, Cp, which simply correlates to temperature here, reaches point 2, small bubbles of vapor form at all points, and rise. As heating continues, these bubbles grow and burst, causing eddies and general agitation. The form is messy at this point, and turbulent instabilities appear in the fluid. If we increase the temperature of the lower wall enough and continue moving away from the initial equilibrium point, we reach a bifurcation. A convection transport appears, and mass movement is established, point 3. Warm particles, near the floor, are less dense and tend to rise, while cold particles, which have less energy, are drawn downward in a convective swirl. The entity moves as a whole. The microscopic world is naturally orderly, and becomes observable from our macroscopic world. The fluid comes together spectacularly, by forming vortexes in the flow, that rotate in opposite directions like gears. These convective cells are an example of a dissipative structure, a term that Ilya Prigogine used to express the fundamental fact that while energy dissipation is generally associated with disorder, it becomes a source of order, far away from equilibrium. In a Bénard convection cell, there are short-range correlations, caused by the interaction between neighboring molecules. But there is also a long-range correlation, between a molecule in an updraft and a molecule in a downdraft. Molecules that have cooled near the cold surface descend to the warm surface, by transmitting information about the condition of the cold surface, thus establishing communication and a control system. Shannon's information theory says that a system that receives information is more orderly, and its entropy is lesser. In Bénard's small-scale experiment, the Coriolis effect can be neglected. It will become enormously important in the movements of larger phenomena, such as winds and marine currents. The fundamental laws of physics are identical in Galilean systems. However, the Earth, rotating around its axis, is not a Galilean system. The Coriolis inertial force, in particular, provides a necessary correction to Newtonian mechanics to account for this. The Coriolis effect, which was negligible in Bénard's experiment, should be taken into account to the movement of all bodies with mass in rotating systems, such as the Earth rotating around its axis. The intensity of the Coriolis effect is proportional to the moving masses. The fictitious Coriolis force deflects the relative movement, but does not affect wind speed. In the northern hemisphere, the Coriolis effect deflects wind to the right. A tropical depression is a localized disturbance, with a low-pressure center. The evolution of a tropical depression is unpredictable. A depression causes winds to converge. They grow warmer upon contact with the ocean's surface, and rise into the atmosphere. Vaporizing seawater plays an essential role in this process. The warm, humid updraft causes clouds to form at high altitudes. A tropical storm is a more violent phenomenon, characterized by stronger winds. It can grow to several hundred kilometers in diameter. Masses of warm, moist air rise towards the troposphere, creating conditions conducive to heavy precipitation and storm development. By tilting the trajectories of air masses joining the depression, the Coriolis effect transforms them into a massive whirlwind. What was once a tropical storm can become a hurricane under the blazing sun of late summer. Far away from equilibrium, the system passes by a bifurcation, with probably phenomena more or less chaotic, before stabilizing in another, more orderly configuration. A hurricane. While a cross-section of a hurricane may resemble the Bernard experiment, the 3D reality is very different. The Coriolis effect drags the entire system into a powerful tropical cyclone. We can use observations made by aircraft and satellites, measurements taken inside hurricanes by reconnaissance flights, and some theoretical concepts to draw a diagram of a hurricane. The order in the hurricane's eye, and in the wall of the eye, is apparent and appears highly structured. When the control parameter of the tropical storm system reaches a bifurcation point, the resulting convection movement that takes place forms a remarkable spatial organization of the system. The hurricane is the most grandiose case of molecular restructuring. Billions of molecules move in harmony, forming gigantic convection cells. Within this spectacular display of spontaneous self-organization, order appears, and entropy decreases. The hurricane takes advantage of this order to become a solar heat engine, providing the motive power that the hurricane uses to grow even bigger. This thermal engine, created by nature, by using the laws of physics, is an anomaly in the Earth's necessary thermal balance. This order, which slows down the dissipation of energy, thus prolongs the life of a remarkable natural phenomenon, but that is harmful for humankind. This hurricane structure is composed of both order and disorder, and exchanges matter and energy with its environment, eventually causing the hurricane to peter out once it loses its source of matter and energy, i.e., when it makes landfall.
Thank you for watching.